Hello, everyone. My name is Kevin, and today I will be talking about clustering algorithms in machine learning, specifically within the scope of unsupervised learning. These methods are incredibly powerful for discovering hidden patterns in data. So, let's dive in. So, to start off, unsupervised learning is a type of machine learning where we work with unlabeled data. Unlike supervised learning, where we know the correct answers, here we aim to uncover hidden patterns or structures in the data. Some common applications include customer segmentation, anomaly detection, and recommendation systems. As discussed in the paper, I'll reference it in the last slide. A rapid review of clustering algorithms by Hui Ying in 2024. These techniques are foundational in fields like marketing, healthcare, and social media analytics. And so one key technique in unsupervised learning is clustering. Clustering involves grouping objects so that items in the same group or cluster are more or less similar to each other than those in other groups. For instance, clustering can be used for market segmentation, image compression, or organizing documents by topic. As noted in the review paper by Hui Ying in 2024, again, I referenced it in the last slide, so feel free to go take a look. Clustering algorithms reveal natural structures in data and are applicable across various domains, including image analysis and anomaly detection. There are several types of clustering algorithms, each designed for different data structures and requirements. Based on the classification from the paper I referenced, algorithms can be categorized by principles such as partition-based clustering, which is known as k-means clustering, density-based clustering, which is known as dbScan, and then hierarchical clustering, which is also known as agglomerative clustering, and a couple other ones that I won't really get into in this presentation. Honorable mentions are model-based clustering, which is known as Gaussian mixture models, and grid-based clustering. So each type has its strengths and limitations. For instance, partition-based methods are efficient but sensitive to outliers, while density-based approaches excel in handling arbitrary shapes. So to start off, k-means is one of the most popular, if not the most popular clustering methods. It partitions data into k-clusters by minimizing the variance within each cluster. The process starts by initializing k-centroids randomly, then assigning each point to the nearest centroid. Next, centroids are recalculated based on the assigned points. And this process repeats until no significant changes occur. Well, simple and fast k-means require us to specify the number of clusters beforehand and can be sensitive to outliers. As highlighted in the paper, silhouette, score, and elbow methods can be applied to help determine the optimal number of clusters, but unfortunately today's presentation won't be enough for us to cover those in details, so I should just mention that they exist and that they can help with solving these problems. And this would be a great example of what a k-means clustering graph looks like. As you can see on the left, that's the raw data, and on the right, there's the k-means clustering. And what you'll see is there are three categories that's differentiated by colors. And you can see the shape is exactly the same as raw data, but the dots are in groups of their own color. And you can see that there's also the cluster centers, kind of like center of mass in physics. you can kind of imagine it in the same term. But basically, yeah, it's divided into 3 colors and into these shapes. And so moving on, we have DBS GAN, also known as density-based clustering. Or if you want to be fancy, you can go with density-based spatial clustering of application with noise. Ooh, mouthful. Anyways, this algorithm identifies clusters as dense regions separated by areas of lower density. It has 2 key parameters, epsilon, which defines the neighbor radius, and minimum points, and it's the minimum number of points needed to form a dense region. DBS scan is excellent for handling noise and discovering clusters of arbitrary shape, but its performance heavily depends on the parameter tuning. According to the paper, density-based methods are particularly effective for high-dimensional data, but faces challenges with uneven spatial data density. And so what you see here is an example of what a DBS scan clustering graph would look like. So what you can see here, very plainly, obviously, is that just like what we mentioned, it is good at detecting outliers. So as you can see, there's like 4 groups of dots with their own individual colors. Yet beside them, there are some of them that's like colorless, or you can call it gray. And those are the outliers. So that's what DBS scan is good for. It's good for data that's not reliable. And so finally get into hierarchical clustering, which is also known as agglomerative clustering. The hierarchical structure in hierarchical cluster builds a hierarchy of clusters by iteratively merging or splitting data points based on their similarity. The process creates a dendrogram, which visually represents the cluster relationships and the order in which clusters are formed or separated. There are 2 approaches in hierarchical clustering. One is agglomerative and another is called diffusive. With agglomerative, we start with individual data points and merge them into clusters. And then in diffusive, we start with a single cluster and split it into smaller clusters. The choice depends on the specific application and the nature of the data. So there is no, not a one that's better than the other. And then with flexible cluster selection, hierarchical clustering provides flexibility in cluster selection. The dendrogram allows researchers to choose the data of clusters that best suits their needs and goals, enabling a tailored analysis of the data structure and relationship. So this is an example of what a agglomerative clustering graph would look like. You would have to separate them into 2. One is the dendrogram and another is the graph itself. As you can see, the dendrogram describes how each sections are divided and being enwrapped or contained into another. And on the right, you can visually see how it's being contained. Yeah, and so honorable mentions, model-based clustering and grid-based clustering. Unfortunately, we don't have enough time today, so maybe next time. Yeah, maybe next time. 2 applications of clustering, I would start off with again, because it's such a good example, it would be customer segmentation. Clustering can be used to group customers based on their purchasing habits, demographics, and other characteristics. This allows businesses to tailor marketing campaigns and product offering to specific customer segments, improving customer satisfaction and loyalty. Second, we have image analysis. Clustering can be applied to identify objects in images, segment images into different regions, and compress images by grouping similar pixels. This has applications in image recognition, medical imaging, and computer vision. And then the third one would be document categorization. Clustering can be used to group documents based on their content, allowing for efficient document organization, information retrieval, and topic modeling. This is useful for applications such as news aggregation, scientific literature analysis, and web search. And finally, we have anomaly detection. Clustering algorithms can identify outliers or anomalies in dataset, helping to detect fraudulent transactions, network intrusions attempts, and other unusual events. This has significant applications in security, fraud detection, and data quality assessment. Despite its utility, clustering comes with challenges. Determining the right number of clusters is not always straightforward. As highlighted in the paper, high-dimensional data can complicate clustering results. Algorithms can also be sensitive to noise and outliers. Moreover, selecting an appropriate distance metric and ensuring computational efficiency for large datasets are critical considerations. Current research trends include incorporating deep learning techniques to improve clustering performance and address these challenges. So to put these into detail and to dumb down what I just said, we have like 4 main challenges you can take as a grain of salt. Feature selection. Choosing the right features to represent data can significantly impact clustering results. Improper feature selection may lead to inaccurate or misleading cluster assignments. And in noise handling, outliers or noise points in dataset can negatively impact clustering performance. Dealing with noise effectively is crucial for accurate cluster identification and analysis. And in parameter tuning, many clustering algorithms require parameter tuning, such as the number of clusters, k and k-means. Finding the optimal parameter settings can be challenging and require careful experimentations. And then cluster validation, evaluating the quality of clustering results is essential. Various metrics and techniques, are used to assess the validity and significance of the discovered clusters. Clustering algorithms are powerful tools for extracting insights from unlabeled data. They have a wide range of applications across various domains, helping to uncover patterns, structure, and relationships within complex data set. While challenges exist, careful consideration of feature selection, noise handling, and parameter tuning can lead to meaningful and accurate results. As noted in the paper, the field continues to evolve with new methodologies and hybrid approaches, making it an exciting area for future exploration. I encourage you to experiment with these algorithms on real-world datasets and explore advanced methods for even deeper insights. So, thank you for your attention. I hope this presentation has provided a good overview of clustering algorithms in supervised learning. I tried to make it as intuitive as possible for perhaps ones that have never really dabbled on this subjects or nearly close to, these kind of stuff. I'm happy to take any questions or discuss further resources for learning about clustering. So let's open the floor for questions.